Okay, to achieve that, meaning that how we gonna remove these zero things, okay, zero element in H. Okay, just again I try to express back our statement here. This is the same part that we have discussed before in the previous slide. Okay, this is your G, and now this is your inverse filtering, and then okay, we try to convert this one, your H here, into F head. So what is F head? Okay, don't worry about the notation there. We just define some new notation there, which is called F head, and F head is 1 over H, your H. Okay, so it's another way around of your H. Okay, that is H head. So why we want to express this one? So now we can see here, if this is my inverse filtering, so if I replace my H with H head, it will become multiplication. Okay, so from the previous expression like this one, okay, this one also in the previous expression, if I replace this one with the H head, it become multiplication of this one. So like what I have discussed before, we want to avoid H equal to 0, or in other words, if we talk about our H head here, we want to avoid our H head equal to bigger number. Okay, just remember that the definition here is H head is UV is equal to 1 over H UV. So the one that we want to avoid is the region where your H okay, the one that we want to avoid is that region, the region of your H UV equal to 0. So in other words, or close to 0. Okay, or close to 0 or 0. In other words, if you talk about H8, which is 1 over H, so you want to avoid something which is close to infinity. Okay, it's another way around, meaning that if we want to avoid our H equal to 0, if you translate into H head, which is the definition of H head is 1 over H, then we don't want to have our H component which is a big number or close to infinity. So that's why in this statement, if you replace, if you go back to this slide, okay, this one, wait, okay, if you go to this slide, okay, if you express it in H head, okay, this one statement, then we don't want this one to go to the to close to a big number or close to infinity, because if this is infinity or close to a big number, then this one become big, okay, which is the one that we want to avoid. So that is where we this is the facts there. Okay, if you want to have your F head close to your F, then make sure this expression is close to 0. So we need to make sure this H head, which is can be controlled, again can be controlled, this n cannot be controlled because that is random. This is the one that we can control. So to make sure this one is close to 0, this is the one that you need to make it close to 0. So if you see the picture here, after you convert from H to H head, the one that is we want is this region. Okay, the fact is similar. Okay, if you talk about H, we want this region, the same region. So if you convert into 1 over H, which is our H head, we want the same region. We don't want the side information here. This one is the one that we want to avoid. The one that we want is only at the center, at the center of the cylinders there. Okay, the same cylinders. Okay, so how to manipulate this thing to make sure that we can remove the element which is not inside the cylinder, is out of the cylinder, which is this one or this one. Okay, so one of the alternative in order for you to manipulate this thing is actually you are cascading your system with ideal low pass filter. If you remember, low pass filter that I discussed before, the ideal low pass filter, it's look like actually the shape is cylinder. So if we can, you know, have some sort of low pass filter, then you can imagine actually this cylinder is actually your low pass filter, ideal low pass filter. So if this is the H, okay, if it is the H, then if you cascade this one, okay, if you have some system like this one, you have H8 UV, okay, that is the one filter. Okay, H head here is after I is defined as this one 1 over H. If you cascade it with some ideal low pass filter, then this one will represent your cylinder here, or the cylinder here, which is actually will remove all the element outside this, outside the cylinder, or this one. Okay, doesn't matter, is it, we can discuss in term of H, we can also discuss in term of H head. Okay, again the objective is similar. We want to avoid your this component become dominant, and one way to do is we want to avoid this thing make it this dominant. And if you talk about the H head here, the one make this one dominant is the one that outside the cylinder. So that's why if we can apply the ideal low pass filter, which is the shape is exactly cylinder, then you can avoid, or you can remove this component at all, or you can also, we can say that you can minimize the domination of this one in this expression. Okay, so that is what happened in this condition 3. Instead of applying the inverse filtering, okay, you also need to cascade the system with low pass filter, the ideal low pass filter, so it will automatically minimize this domination, or okay, this thing, it will minimize this one and make this one become dominant. Okay, so that is the good things about condition number 2 and condition number 3. You can see that condition number 3, we also if you back to our discussion here, okay, we go back to the summarization here. Okay, you can see that in condition number 1, okay, we in order for us to, you know, remove the noise, we have a long discussion, we have learned about a lot of filter just to tackle the noise. But when you learn the condition number 2 and number 3, okay, the restoration block here, restoration filter block here, you can replace it by simply applying the inverse filtering. Okay, inverse filtering meaning that this is the one that called as inverse filtering. Okay, but in condition number 3, of course, you have a 2 component inside the inverse filtering. It should be 1 over H, which is this one is inverse filtering, and then we have another block which is called ideal low pass filter. You cascade with these two, then you solve everything without you know, applying the filter that we learned before. Because what happened is actually that is the good thing about inverse filtering, because in inverse filtering, if you go back to this slide, okay, that have been proved, and that have been proved by this, we after we discuss about this expression. Because after cascade with low pass filter here, then surprisingly you make this one minimize and this one become dominant. In other words, it seems to be you are manipulating this one. By manipulating this one, doesn't matter, or regardless what type of noise affected your image, if this noise is multiplied with something which is close to, you know, close to 0 or small number, then it's not dominant, anymore, it's not dominance anymore in this expression. So you don't have to remove at all by using the filter that you have learned before. Okay, that one is only specific for condition number 1, where the image is free from degradation function. But if the image is affected with degradation function, then by simply applying the inverse filtering, actually you manage and cascade with low pass filter, then actually you are automatically removing this component, and you don't have to think about this noise anymore because it have been removed or destroyed by manipulating this element here. Okay, so the next slide is just a discussion about after cascading. Okay, this one this one just showing you how we do the cascading. Okay, of course when you cascade to filter, it become a multiplication of this one and this one. Okay, you are multiplying this one and this one. So this is the one that I call as my H new. Okay, my H new here. Sorry, H head new. Okay, this one multiply with this one. So it's become something like this. And then again your H new here, after you, if you express into this equation, it's look like this again. The one that out of the cylinder will become 0, the one that is inside the cylinder will become the remaining H head. Okay, the one that out here becomes 0, the one that inside here will remain the information that you have you obtain from your H head. Okay, so that's how you express this equation. Okay, that's why the equation look like this, or the expression look like this, meaning that anything inside the cylinder or inside the this one should be, I think, D naught. Okay, this one now become R. You can put R or you can put D naught as the previous chapter. The previous chapter you use a D naught there, a cut-off frequency. So meaning that anything below the cut-off frequency or inside the cylinder, you remain the H head. So that's why this one multiply with 1, so that's why it's become that the same number. So anything outside the cylinder, this one multiply with 0, so that's why it becomes 0. So that's how it look like. Okay, so that is the concept. So and then if you the next slide is just discuss about what happened is actually in practicals. Okay, let's say this is your original image. Of course this is not your F, this one is in frequency domain. This one should be, this one should not capital F, it should be F XY. But after that, if you apply the Fourier transform, it become the capital F there. And then assume this image is, this image is okay, just assume that this is the one that we cannot access. So this one is just, they do some simulations there, so that's why they try to blur the image. That's why it become G there. And then that G is actually is blurred by this model. Okay, this model. So once you know this blur by this model, then so that's why you also know this one. Okay, because this one is simulation, so don't confuse. In practical, you don't know your G, you don't know your F, but this one, because they do the simulation, that's why they just simply generate the blur image that is generated by this blurring model. They are using mathematical modeling approach. Then this is your G. So what you do, this one is the result after, okay, this one is the result after you directly apply inverse filtering. Just assume that, okay, this one, this case I forget to mention, just assume that this image as well is also affected with noise. So imagine if this image here is affected with both blurring degradation function as well as noise. So what you do is actually, if you simply divide your G with your H without low pass filter, without cascading low pass filter at the back, this is what happened. Okay, this one is the image after it become F. Okay, it's not capital F anymore. This one is spatial domain. Okay, this one is spatial domain. Okay, if you get this one and you apply the inverse filtering, then this is how it look like. Okay, you cannot see anything there. Okay, this is because without low pass filter, the noise component, okay, this one is still dominant. Okay, the one that this one is still dominant, because we don't have a low pass filter. Yep, this one is still dominant without low pass filter. So that's why, because of this, when you convert into your spatial domain f8, then you cannot see anything there. But when you apply when you are cascading with low pass filter, then you can see there. Okay, this one is the after you applying the low pass filter with the cut off frequency of 40 or radius 40 or the radius 40. Okay, and then this one is 70 and this is 100. You can see there, by the time you increasing the size of the cylinder, then the noise already, you know, there's a effect there. Now your image is already affected with certain noise. Okay, the reason why this happen, you can go back to this one. Yep, this one. Okay, if you see these pictures, if you increase the radius of your cylinder, become more and more bigger, then you already include, okay, if you this one, okay, if this cylinder you increase the radius, let's say you put a little bit large than before, then what happen? If this one become bigger, then you also include the one that you don't want, which is this one, because this one is already in big number, or because of this big number, that will make this one become dominant. Once this one become dominant, that's why, you know, this image is already affected with certain noise. Okay, because your noise is not it's not equal to 0, or it's not close to 0 anymore, it's become dominant. So that's why it's even you can see the image of this person, but this image is affected with that noise because of that effect. So that's why you need to reduce, you need to vary your radius until you find out the noise here have been removed like this one. And also, of course, we don't want to have a small radius, because if you have a small radius, okay, if you remember, the lower the cut off frequency, that's mean only a small portion of frequency component will be passed through the system. So in other words, if you reduce your cut off frequency, okay, this one is also related to chapter 4. I already mentioned that if you reduce the cut off frequency, meaning that you are only allow a very small frequency component to be passed. So if that component is, you know, dominant at the output side, in other words, then that image will become more and more blurred, because the low frequency component is very dominant at this image. So that is what happened here. Okay, the image become blur because you are removing the high frequency component, or the sharpness of the sharpness component inside the image. Okay, remember when we talk about the high frequency component in image is related to the sharpness component, or the sharpness component of the image. Okay, the sharpness of the image, because the high frequency component represent the sharpness of the image. So if you remove almost all high frequency component, this is what happened. So that's why we don't want our cut off frequency to be very small, but we don't want our cut off frequency to be very big until it already also include the noise. So that's why we need to tune in certain value. Okay, for example, the best in this example is 70, because that is the point where actually you already remove the noise, and at the same time you don't want to reduce this less than 70, because the more you reduce the value, the more blur that image that you get, because we want to remain the high frequency component inside as many as possible. So that's why 70 is the best. Okay, so I hope that you can understand about the discussion in this thing, and this is the end for the end part of chapter 5. Also, as the summary, again, let's go back to this slide. Yep, this slide. So in chapter 5 we learn about the restoration, and then we talk about 3 condition 1, condition 2, and condition 3. And then we have a long discussion about the condition 1, because that is the one a little bit challenging, because once you don't have any degradation function, then the only degradation factor that affected your image is noise. Then because the noise is random, that is why it's very challenging, because we cannot represent it in mathematical expression. Then because of the random behavior, then one way we need to model the probability distribution function, and one way to do that is by take the plane surface and then you generate the histogram, because from the histogram, then you if you normalize the histogram, actually that represent the PDF. Once you know the PDF, then you know the type, the noise model affected your image. Once you know the type of noise affected your image, then you know which filter is suitable to be used to be put in this block. Okay, either is from mean family filter, or statistical order statistical filter, or any adaptive filter. You can, it's depend on which noise that you want to tackle. Okay, that is the challenging about condition number 1. But condition number 2 and condition number 3, in order to solve, or to put something here, is not very challenging, because we only have one solution, which is called inverse filtering. Okay, inverse filtering, this is called inverse filtering. But the step for condition number 2 and condition number 3 is similar. You need to estimate your H. Okay, because like the condition number 1, we want to estimate our noise model, and this condition number 2 and 3, you need to estimate your H, or model your H. So there's a 3 way to do that, which is called observation, experimentation, and mathematical modeling. Okay, once you get your H, then this block over here, just apply the inverse filtering. This is what we call inverse filtering, because once you already know your H, then you just get, you know, your G here, multiply with 1 over H to get your F head here. Of course, this one at the end you need to convert into this using inverse Fourier transform in order for you to see. And same goes to condition number 2, and I'm sorry, condition number 3. If the image is affected with both degradation function and noise, you also tackle with inverse filtering concept, but a little bit modification. Instead of only applying the inverse filtering, you need to cascade with ideal low pass filter. That is for the purpose of minimize the dominance of minimize the contribution of the noise component, so now it become not so dominant in that expression. Okay, so that's why, that's the reason. So now that is how we automatically remove the noise without thinking about the filter that you learn in condition 1. Okay, by applying the low pass filter, you will automatically remove that noise component inside the expression that we have discussed before.